So now that we know all the 3 different types of bonds, I thought we would have this amazing fun way to summarize the differences in the 3 types of bonds. You guys, look at this. What kinds of elements? What happens? What is the electrostatic attraction? What is the structure? What are the names for this type of bond? Relative strength, melting point, boiling point, state of matter, room temperature, conductivity. These were the things that on each one of our notes sections for each one of my bond types, we really hit home. So now it's going to be really great to be able to have it all kind of summarized in one spot. So I thought, since we're, oh my gosh, I thought more coloring, let's do more coloring. So we know that metals are red, non-metals are blue. So I thought we could color our little headings on our types of bonds, maybe the colors of the elements that are involved in that type of bonding. So metallic bonds are going to be red, right? I'm gonna move this paper so I can get it colored a little bit better. Just metals make up metallic bonding. Okay. Yes. My ionic bonding, I have a metal cation and a non-metal anion. So I will color the first half red to represent a metal cation. Okay. And the second half, I will color blue to represent the non-metal anion. And then finally my covalent bond, which we now know is non-metal, so that will all be blue. Look at this, you guys. Look how fun is this for us. Okay. Not the best coloring job, but that's okay. It does not matter. All right. So now we can actually see our colors, and you can tell me what types of elements are involved in this bond type. So what types of elements for metallic bonds? Y'all, those are metals. What types of bond for ionic? We have metal and non-metal. And then what type for covalent? We have non-metals. Yes. Okay. What happens with the electrons? In a metallic bond, they delocalize their electrons. So delocalized. What happens in an ionic bond in the electrons? They are transferred. And then what happens in a covalent bond? They are shared. So, oh my gosh, boom, boom, boom. Look at all this. This is some good stuff. And specifically in my ionic bond, it's transferred from the metal to the non-metal. So if you want to draw a little picture showing the electrons being transferred, that may be helpful because we know we get that positive and that negative from that little transfer. Okay. All 3 of my types of bonds, no matter what they do, there is an electrostatic attraction. Once again, electrostatic attraction is between a positive and a negative, right? So in each type of bond, the positive thing and the negative thing may differ. So let's summarize what the positive thing is for each and what the negative thing is for each thing. That's a real scientific term for me. So in my metallic bond, all of the metals delocalize their electrons. So the positive thing are your metal cations. And the delocalized electrons are the negative part of the electrostatic attraction. So we will say, and delocalized electrons, which are my negative. Okay, so there's your electrostatic attraction between those two positive and negative things. Okay, for my ionic bond, as a result of this transfer, you create a positive metal cation and a negative non-metal anion. So my electrostatic attraction is between the metal cat ions, so those are my positives, and my non-metal anions. Amazing. And then my covalent one is kind of the weirdest of my electrostatic attractions for me to visualize. But remember, with this shared pair, each one of the nuclei, each nucleus on each atom is pulling on those negative electrons. So we're going to say the positive thing is both nuclei. Nuclei is the plural of a nucleus. And we know a nucleus of an atom with protons and neutrons is overall positively charged. So the nuclei and the shared pair of electrons between the two atoms. So that is my negative thing. Look at how nice this is already for us. I'm very excited. Okay, what is the structure? So each one of these different types of bonds have a unique structure, right? So my metallic bonds are with the delocalized electrons swimming around. That is the sea of electrons. So we're going to write sea of electrons up here on top of this box. Sea of electrons, right? That's my sea of electrons. And we're going to draw a picture of what this sea of electrons looks like. It is the positive metal cations hanging out, right? And we are going to draw little minus signs showing those electrons floating around, right? And so we're going to label one of the positive guys. I'm going to zoom in a little bit so we can see a little bit better. This one is a metal cation. And these dashes represent my delocalized electrons. So here we've got a nice little kind of flowchart picture of what is going on to create this metallic bond, which is very satisfying for me. Okay, so for my ionic bonds, where it's transferred between the metal and the nonmetal to create a cation and anion situation, that creates that crystal lattice, right? That alternating structure of positive and negatives, right? So we have a crystal lattice. Okay. Now my crystal lattice is going to look a little bit like this. Where here are all my ions that were created from a transfer, and they will alternate positive, negative, positive, negative, positive, negative. Because like charges repel, right? So they will be oriented in a way to where alternating charges will be in contact with each other, right? So you get this giant crystal lattice structure. So go ahead and label a positive guy a cation and a negative guy an anion. Yes? So that's our crystal lattice. And now for our covalent guys, so they're literally sharing their electrons and overlapping electron clouds, right? So for this one, it's not a pretty little structured thing, but we do have all of these like little weird, Vesper 3D shapes. So that's what we're going to write here right now. And we haven't learned about, I call it VSEPR because if we're going to look at the letters in this little alphabet here that we've got here, let me show you. VSEPR stands for valence shell electron pair repulsion. So if I'm reading that, that says VSEPR to me, but everybody else in this world says VESPR. And I cannot, you guys. So I don't know. I cannot. Anyway, so I'm sorry if I say VSEPR because my brain will not allow me to do anything different. That is a big tangent. So we're going to say VSEPR 3D shapes. Okay. So if I wanted to draw kind of a picture of my water molecules, kind of hard to visually draw a VSEPR shape, but you get the idea. And this kind of shows you the difference between my metallic, ionic, and covalent structures, showing these molecules here. Cute. Okay. Now the next section here says names for this specific type of bond and some examples. So we call something in a metallic bond metals. There's not anything super fun about this. Metals. Okay, so anything on my periodic table that is a metal: sodium, magnesium, zinc, aluminum, lead, copper, my alloys, which are mixtures of different types of metals. You guys, that's why metallic bonding doesn't have a specific door in our naming booklet, because I'm literally just naming what the element, that metal element is in that metallic bond. So that is good for me because I do not have to do a lot of complicated stuff for that nomenclature. If I move to ionic, we call an ionic compound that lowest whole number ratio of how many cations to anions you have in a crystal lattice structure. We call that a formula unit. Okay, so some examples of formula units. These are my ionic compound formulas where we do the crisscross and we see how many of each ion we have to each other. What's the ratio of those things, right? So we have NaCl. That's an example of sodium chloride. Another formula unit of an ionic compound is MgF2. We could have a real complicated one with like a transition metal and maybe a polyatomic ion. Let's do zinc nitrate. Yep. So once again, I'm looking, all my examples of metallic bonds are all metals on the red side of my staircase. All of my ionic compounds have a red and a blue. So when we get to covalent, hopefully we're only looking at blue nonmetals around here. So we call covalent compounds molecules. And my guinea pigs are squeaking back there, so they're getting excited about some molecules here. Okay, so examples, we got a classic one, H2O, we've got CO2, we've got sugar, C6H12O6, anything that's a nonmetal from my periodic table. Very satisfying. We've got metals, formula units, and molecules. Okay, relative bond strengths. Okay, so comparing my metallic, ionic, and covalent, my metallics are my weakest. Okay. My ionics are, we would say, I guess, medium strength, so medium. And then my covalent is the strongest. And when we say strongest, specifically the bond in between the atoms, that shared pair of electrons. So we are going to call that the intramolecular force. And keep in mind, we talked about the intermolecular forces, the forces of attraction that would hold two molecules together. That is actually even weaker than my metallic bond. So if you want to, let's do that over here. Let's write over here, past metallic here. Let's write, in parentheses, maybe covalent inter. Okay? This is really kind of ranking the overall forces of attraction. Yes, these guys over here are the bonds, but this is also a force of attraction that holds covalent molecules together, and that is the weakest, which is why some of these properties will start to happen, okay? So here we go. Melting points and boiling points. Y'all, we wrote down for our metallic bonds that they have high melting points and high boiling points, because of a really strong electrostatic attraction here in this sea of electrons between the metal cations and the delocalized electrons. Ionic compounds, they're even stronger. The metallic compounds are metallic bonds, so we would say that their melting points are, whoops, I wrote boiling point first. Their melting points are higher, so I'm going to put like a double arrow, just means even higher. And then higher, that is a terrible arrow. Get it together, Sabatka. There we go. Yeah? And then you're like, cool, strongest, even higher, 3 arrows she's going to go. But no, remember we wrote in our notes that covalent compounds, y'all, it didn't take a lot of energy for them to melt and boil. Not because of those intramolecular forces, it's because of these weak guys over here. So we get to write an arrow down. They have low melting points and low boiling points. And we are going to write over here that this is due to the weak, that's a W, weak intermolecular, y'all, I'm gonna make this a different space. I'm gonna write inter dash molecular forces. So inter, okay? So this business is all represented because of this, which is super cool. Okay, what state of matter are they at room temperature? We're gonna say for my metallic stuff, y'all, they usually solids, unless you are mercury, but we're gonna write usually solids. at room temperature. Ionic bonds, also usually solids. My covalent compounds, they can be anything. If I got sugar, y'all, sugar is totally a solid at room temperature. I got water. Water is totally a liquid at room temperature. And I've got carbon dioxide. He's a gas at room temperature. So I can have the whole spectrum here. So I got solids, liquids, and gases. Once again, this is probably due to these strengths, right? Relative strengths. And then finally, this is my favorite section. So conductivity of electricity. You need mobile charges. So we're going to actually write that here. Need mobile charges. Mobile charges in order for this to happen. Well, the cool thing about my metallic bond situation, you guys, is, oh my gosh, look, there's always mobile delocalized electrons. Electrons have a charge. They are negative. They are always mobile. So we would say metallic bonds are good conductors. Good. In all states. In all states. And when I say states, I don't mean like the United States of America, like Texas and stuff. I mean like solids, liquids, and gases. So we're going to say solid, liquid, gas, etc. Right? That's a terrible etc. It's fine. You understand what I mean. Okay, and the reason for this is they have mobile electrons. Okay, mobile charges in this case are my mobile electrons coming from my sea of electrons up there. Now, my ionic compounds, they're sometimes conductive and sometimes not conductive. So they are good conductors, but only under certain conditions. So we're going to break this up into two sections. We're going to write good when they are liquid or aqueous. Because when they're liquid or aqueous, if I have my ionic compound here, if this is like sodium chloride, if they are liquid, they are able to move, right? That crystal lattice is not so rigid. If they are aqueous, we know ionic compounds dissociate in water. So now they are mobile in water. So mobile charges, we can conduct electricity. So we're going to say mobile ions. So here are my mobile charges, okay? But we're not always a liquid or an aqueous when we're an ionic compound. A lot of times we're solids. And if we are solid, that crystal lattice is stuck together tight. Those ions, be they charged, do not move. So we're going to write poor when they are solid. Okay? And then finally, my molecular compounds, my molecules, y'all, they are poor conductors in all states. Poor. In all states. Solid, liquid, gas. Okay. The last thing I want to kind of maybe down here on the bottom is we will get into how to draw Lewis dot structures for my covalent compounds here in our next lesson. But we've practiced drawing electron dot structures for ionic compounds before, and I kind of want to show the difference between what an ionic one and what a covalent one looks like. Metallic bonds, you do not matter for this, so we are going to ignore you. So if I wanted to draw an electron dot structure for sodium chloride, remember, we're going to show what happens after that transfer of electrons. Sodium would have lost all of his electrons. He's transferred it over to the chlorine, and that means chlorine will have all of his full shell of 8. So that would be a dot structure for ionic compounds. Now, covalent compounds, they're not just like stuck together. They are going to be a shared bond pair. So what that actually means for me is if I were to draw carbon bonded to 4 hydrogens, carbon and hydrogen, they are all nonmetals. You're going to actually see this. This would be a Lewis dot structure for covalent molecules. So here's the difference of those, and that is what we're going to get into on our next lesson. But y'all, this is so nice and satisfying. Just have everything just ranked in a flowchart of how your brain processes and creates all these amazing properties. So this is probably the most important takeaway thing from now our 2 units that we've gotten into with our bonding. But this is great. Congratulations on learning the 3 types of bonds: metallic, ionic, and covalent.